Hello, everyone, and welcome. My name is Liz Pimper, and I'll be your moderator for today's WJE webinar, What's That Sound? Building Noises and How to Stop Them. During the next hour, WJE engineer Jarkko Simonen and WJE architect Sylvan Cambier will explore the noises buildings make and what causes them. They will explain WJE's methodology for finding the sources of noise and for diagnosing the causes. This presentation is copyrighted by West Jenny Elstner Associates. And now I will turn it over to Jarkko to get us started. Jarkko?
Thanks for the introduction, Liz. And thank you everyone for attending our webinar on identifying sounds that are generated by buildings and hopefully how to find the cause of the sound and how to stop them. This webinar is intended to provide some background on why some buildings generate noise, and more importantly, how do we identify the source of that sound or that noise. And we will also talk about what are the common sources of sound generated by buildings and how we can try to mitigate the source once we have been able to identify it. And also we'll talk about a little bit about how to predict some conditions that are common in buildings and can cause sound. And with that, I'll turn over the webinar to Sylvan Cambier to give a little background on sound and typical sources of building sounds.
Great, thank you, Jarkko, and welcome everyone. So let's talk a little bit about understanding what we mean when we say noise. We're going to use the terms noise and sound interchangeably here, but let's understand what is noise and some ways that we categorize noise in buildings. So noise isn't inherently a problem. It could be pleasant or welcome. So applause and water flowing and rustling leaves, even a baby laughing could be a pleasant noise. Of course, noises can be irritating and distressing, and that's really more what we're focused on here. The classic examples, of course, would be nails on a blackboard and honking horns. And this is one we'll come back to again, which is an unknown sound, right? An unknown noise can be distressing if you don't know what's causing it, and that's frequently the case in buildings. We also have the category of quiet but frequent, so dripping faucets and creaking floorboards, squeaky hinges. These aren't particularly loud noises, but they're recurring. And then there's the loud but infrequent type of noise. So an explosion, and a single incident of sound, broken glass, earthquakes, these are loud but infrequent noises. So in the quiet but frequent category, we talk about those like ticks, pings, squeaks. These are persistent noises that are sometimes problematic, and they may be annoying or irritating or distracting. In the loud but infrequent category, we're thinking more like bangs, pops, and booms. And again, we're talking about persistent noises here or single occurrences, but they're usually problematic because they're startling, disruptive, or unsettling. If it's a single occurrence, it's much harder to diagnose. If it's a persistent noise, it's something that we can come and observe and find the location of. We're also going to be discussing sound and noise in terms of sound pressure. So there's some basic metrics for measuring sound pressure. SPL is the abbreviation for sound pressure level. It's measured in decibels. And the range of decibels from quiet to loud or even painful is between 0 and about 140 decibels. So these are some examples of what types of noises land in different decibel ranges. And the typical background sound pressure level that we find in a building is somewhere in around, give or take, 40 decibels. Could be a little less or a little more. And we often are going to be measuring that as sort of a baseline for understanding whether a noise is going to be noticeable in the context of that ambient background noise. Okay, so noises in buildings. They almost always start as a vibration in a solid material, and And we're talking about structure-borne noise when we're talking about noises through solid materials, but our ears are intended to hear sound that's traveling through air, an airborne noise. So that's typically how we hear it. We do feel the vibrations in the building, especially the lower frequency vibrations are more easily felt. And if you're touching solid objects, your ability to hear that structure-borne noise is going to be enhanced. So we see vibrations turning into noise through all variety of building materials. Could be curtain walls, could be punched windows, roofing structures, cladding systems in general, precast systems, structural steel frames experience a fair amount of thermal movement. Wood structures also experience thermal movement. Of course, if you hear a fractured PT tendon, that's a very disturbing sound. It might be a single occurrence, we hope. People walking around on floors. And then there's other sources of noises in buildings that are very common and are fairly well studied, but are not the topic of our presentation today, like mechanical equipment and plumbing systems. And then, of course, there's a whole category of studying noises in buildings where we're talking about sound privacy, right? People, ambient noises, being adjacent to freeways or other noise sources. And those are not what we're talking about today. We're really talking about the building components, the structure and the cladding systems. So just to recap, we're talking about frequent or persistent noises. We're talking about noises related to the cladding or the structure, and noises that we have identified as disturbing, and that can be subjective to the person experiencing the noise. We're not talking about single occurrence noises because we just can't trace those down if there's no recording of them. We're not talking about mechanical systems. We're not talking about noisy neighbors or sound privacy. I'm going to play for you some sample clips, audio recordings of different types of pings, pops, and clicks that we hear in buildings. What I'm about to play is from a wood structure experiencing thermal movement. Short audio clip here.
I have to laugh at my younger self.
So we're also going to give you an example of what a curtain wall, aluminum curtain wall or ribbon window wall system can sound like. You can hear there's a distinct quality difference in the sound, right? But a similar type of pinging and popping sound. This is something we're all probably a little more familiar with. So dynamic live load, like people walking across a floor system, can create not only creaking sounds, but also snapping and popping sounds. And here's a recording of what that might sound like. This is an interesting one. So wind loads, especially on tall buildings, right? We can see quite a bit of movement in a windstorm in a building, and that can create noises as well. So this is a recording from the Burj Khalifa, which is the tallest building in the world, and it sounds a little bit like a ship at sea. Okay, so there's a variety of noises a building makes, but they're all similar in that this popping, squeaking, ticking sounds, sometimes getting into the realm of banging. And one thing that we're going to talk about frequently in this presentation is that there's vibrations, right? And then there's the sound itself. And I want to use the example of a piano to illustrate how the source of the sound in a piano is not the string, right? That's the source of the vibration. Without the sounding board in the piano, if you pluck the string, there's not much to hear, right? But when you connect it to a surface that resonates, and that surface can transfer that vibration into the air, then you hear it. And the shape of that resonant surface really affects the volume and the perception of the vibration, right? So when we're looking for the source of a noise, we're interested both in the sounding board, right, what's transferring that noise to air, and we're interested in the individual source, what string is being plucked to create that vibration. When we're trying to triangulate the source of these vibrations, one way to understand this methodology is that it's very similar to the way we look for the epicenters of earthquakes. We understand how fast these waves and vibrations are moving through a solid material, and we can, using different sensor locations to monitor the vibrations and understanding when that wave arrives at each sensor, we can work backwards to find the epicenter of the vibration. So you'll see diagrams that look similar to this that we use to track the source of vibrations. Industry standards for understanding how to measure noises in buildings. This is a blank slide because there really isn't much out there for the types of noises we're talking about. Now, for steady state type sounds like mechanical systems, there are standards, and the ANSI S12.2 is a criteria for evaluating room noise, but it's sort of tangentially applicable to the types of ticks and pings that we're talking about here. So that's okay. We've got methodology to work with, and there are a variety of tools that we can use to assess noises in buildings, but there's not a lot of industry standards in place for us to rely on for that. I'm going to hand this back over to Jarkko. He's going to talk about some case studies that we've worked on and some real-world problems.
Hi, thank you, Sylvan. Yeah, let's take a look at how we use the information that Sylvan just provided to identify the source of the sounds in buildings. So as Sylvan explained, sounds are caused by vibrations. For us to detect the building-induced sounds, we use these small accelerometers, which is shown here on the left-hand side of the screen. And these accelerometers are very sensitive, and they can pick up the slightest vibrations in the building elements. And these vibrations are generally what cause the sound that we hear. So to use these accelerometers, we place them onto the building elements in a known pattern, kind of as seen here on the photo on the right. The accelerometers are highlighted by the red circles, and they're placed onto this window curtain wall. And the idea here is to monitor that wall to pick up these accelerations. You can also see on the right-hand side, there's a circle, there's a tripod, and on top of that tripod, you can't really see very well, but there is a sound meter, very much like the one here circled on the left. And we couple the accelerometer readings with these, with the sound meter readings to try to correlate the acceleration that we see to a sound. And to log all of this data, we generally use a portable laptop that's then connected to a multi-port data logger, and the data logger captures the sound or the information from the accelerometers and from the sound meters and transmits to the laptop. Having the laptop on site is very beneficial, especially during the beginning stage of a project, because that way it allows us to see the response from the accelerometer in real time, and also be able to correlate that to also hopefully the sound, if we're lucky enough to be able to hear that sound while we're actually on site. And you can see there the accelerations are that the accelerometers pick up basically look like little mini earthquakes. And here on the right-hand side here, there's a typical view of the plots generated by, in this case, there are 8 accelerometers installed. And as you can see here, 6 of them are producing or excited to produce an event, and the other 2 are not. And although we can look at all this stuff in real time, we typically set up these systems so they can be logged and viewed remotely. And this is pretty important because most of the time it takes multiple days to be able to log enough events to be able to get a good idea of the source of the sound. And we also set up the processing so that there's some known thresholds that trigger an automatic save on the events. That way, we don't have to go back and relive the events second by second and try to capture every sound and acceleration, which would take forever. So now let's take a specific project which we completed recently to try to identify some disturbing sounds. This project was a high-end residence with a terracotta rain screen cladding. And the rain screen cladding is more of a commercial type product that you'd see on high-rise buildings. And you can see this cladding here in this photo. And issues came up pretty quickly after construction, with the building making a bunch of clicking or popping type noises throughout the day. And then also coupled with these clicking noises, there were some booming type noises that the owner heard during the night. And the owner was pretty annoyed, especially with these booming type sounds, because they were so loud that they would wake him up during the night. And although this particular building was a residence, it was constructed much more like a commercial building, and it consisted of a structural steel frame, which was then connected to infill wood framing as well as plywood shear walls. So initially, the sounds were thought to be caused by the rain screen cladding, and you can see here on the photo on the right as well as the details on the left. The system is very complicated and has a bunch of different parts, which include the terracotta panels, which were then connected to these horizontal aluminum rails, which were then connected to vertical hat channels that were then fixed to the actual wall. And then there was also these metal springs that were placed between the terracotta panels and the horizontal aluminum tracks to keep the terracotta panels under tension so they wouldn't clank during a wind event. So with all of these points of contact, there is potential for friction, and anywhere we have friction, there is a potential to cause sound, or if anything slips, it can generate sound. So as you can see with this type of details, definitely multiple points that could cause that sound to occur. So in addition to the rain screen system, I think I mentioned before, this was a very complicated type of construction. So it also included a structural system consisting of a steel frame, which was then connected to some wood framed elements. So in this photo, you can see, or this diagram, you can see the steel frame elements highlighted in red. And then there's also a detail of one of the roof beams, which shows all the wood elements connected directly to the steel beam. And just as with the rain screen, all these multiple parts and all these multiple connections are prone to generating noise. Anytime there's a slip or some friction occurring between these different elements. So, known with after the documentary review and kind of idea of what the building consisted, we were tasked with kind of trying to figure out where is the source of the sound coming from that the owner is hearing. So to do this, we installed a number of arrays, accelerometer arrays, on different parts of the building, interior and exterior walls. And the hope was that with the installed arrays, we could record enough sound events that we could then use to pinpoint the source of the sound. Pinpointing the source of the sound in a building is very similar to pinpointing the epicenter of an earthquake. Basically what we do is we identify the start of an event of each accelerometer. This is shown by the vertical blue, yellow, and green lines on the figure on the left. So each one of these vertical lines coincide with the initial point of where that particular accelerometer was first excited. And then we assume that the vibrations travel at the same speed to each accelerometer, and then going back in time from each accelerometer's initial point of excitation, we can draw circles that estimate how far that particular vibration could have traveled in a given amount of time. And then the intersection of all these circles identifies the origination of the vibration, and then the vibration is then thought to be the source of the sound. So in this particular example, the intersecting circles coincide directly with one of these metal springs that was located between the terracotta panels and the horizontal cladding. So for this, we would attribute the sound that we were hearing coming from that metal spring sliding across that terracotta panel. So in conjunction with triangulating the source of the sound, we also look at the amplitude of the sound and then try to correlate that amplitude to the waveforms to try to figure out if there's any patterns. So this is a typical sound recording with the sound amplitudes taken from afternoon and then to the next morning. So I think this recording starts about 3:30 p.m. and goes to about 9:30 a.m. the next day. And you can also see from this, and the sound amplitude is shown by the orange dots here. And you can see here just an example. So about 7:30 p.m., the background amplitude of the sound is much higher. It's about 30, just under 30 decibels. And then about 7:30, it drops down to about 20 decibels. And this drop is likely attributed to the HVA system running in the building. And what's interesting about the data is that the size of the acceleration doesn't necessarily coincide with the amplitude of the sound. So here the two vertical arrows depict two accelerations, which are shown there on the bottom with the black dots circled in red. Two identical acceleration events. As you can see here, the decibel level difference created by those two events is very large, about 7 to 8 decibels. And also, it's important to note that not all the sounds picked up by the microphone are generated by the area that we are monitoring with the accelerometer. So there's a lot of extra noise that's included in these that are not specifically caused by the area that we are monitoring. So it's a little time intensive to go through and try to correlate a specific acceleration incident to a specific sound level. But we were lucky enough that we got, in this one particular evening, we got several events that we were able to correlate to a specific acceleration event in the accelerometers. So with the number of sounds correlated to waveforms, we're able to then look at those waveforms. So now we know what the sound sounds like, and now we can correlate that sound to a specific type of waveform. And for this particular project, we were able to determine that there was actually two different types of sounds. One was generated by the rain screen, and then the other type of sound was created by something else. So you can see here that on the rain screen side, which is shown on the left, only the accelerometers that were located on the exterior side of the building were excited, and there was nothing occurring here on the bottom sensors, which were located on the interior walls. So I'll play a sample sound of the rain screen, and in this particular clip, there's actually two popping sounds in the very beginning, and then you can also hear at the back end of the recording there's some construction noise in the back. Gives you a little bit of an idea of the amplitude of what we're dealing on site. So hopefully everybody heard those little pops. And as I mentioned, those pops were only picked up by the accelerometers outside and not from the interior. So conversely, many of the sounds that we heard at night excited both the interior and exterior sensors, and the waveform was much different. As you can see here, the waveform had kind of multiple peaks very close together, and on the last voice, on the sound sample, you could hear those two pops, and those two pops are probably separated by a second. On these waveforms, we're looking at, a tenth of a second or 100th of a second. So these pops are a completely different type of acceleration. So I'll play a sample of this second type of sound, and hopefully you can hear the difference. On this one, these were recorded on the inside of the building, and you can kind of hear a faint cricket chirping in the background. And you can also, hopefully that'll give you a little bit of more reference on the sound amplitude. You should be able to hear a distinct difference in the type of sound. One is more of a pop, and this one is more of a kind of a crackle sound. So hopefully everyone was able to hear those differences. So based on a review of the acceleration data and review of all the sound amplitude data, our investigation concluded that the cladding did make noise, but the loud booming noises that were most disturbing to the owner were not related to the cladding. The cladding was very frequent noise, on average about 2 pops a minute, and they generally correlated with exposure to sun. So the cladding sounds mostly occurred during the daytime when there was sun exposure on them. And then the loud nighttime booming noises, we correlated that to thermal expansion and contraction of the structural steel beam that was located along the roof and how it was connected to the plywood framing. And to confirm our findings, we actually built a kind of a simple finite element model shown here on the bottom right there. And you can see that the top side of that wall is expanding, and that's caused by the thermal expansion of the steel beam. And as that steel beam expanded, it's dragging the plywood shear wall that's connected to it and causing all those nails along the perimeter of the shear wall to shift and pop. And that's what we attributed the large booming sounds to. So then let's take a look at another recent project. Similar thing, sounds. This is a multi-story facility, and the sounds were so loud it was actually distracting to the employees, and that's why we were called in to try to figure out kind of the source of the sound. And typically the sounds were most disturbing during warm summer days when there was full sun exposure on the south-facing elements of the building. So this particular facility consisted of a multi-story building that was constructed with a steel frame and that supported a precast curtain wall system. And the curtain wall system is supported by multiple steel connections that attach the curtain wall to the steel framing. These connections are shown here on the right. And the connections were configured such that each precast panel had a fixed connection on one end of the panel and then a free connection on the other end. The connection detail for both types of connections was the same. The only difference was that in between these two brackets, there is a steel shim plate, and in the fixed connections, that shim plate was welded to both brackets, the top and bottom bracket, while on the free connection, it was only welded to one side, allowing that other bracket to slide on that shim plate. And in some areas, the curtain wall was replaced by this ribbon window system to allow some light to get in the building. And windows were continuous and were pinned along their length of the precast panels along the top and bottom frames. And based on discussions with the building occupants, there wasn't really a consensus on where the noise was coming from. Some people thought it was the window, and some people thought it was the steel frame. So to investigate the source of these sounds, we again installed a network of sensors on both the ribbon windows and precast curtain wall panels. We did this at multiple locations at different floors to try to pinpoint the source. But here, this slide, we show a typical sensor layout. We include 16 sensors, which are the accelerometers, and they're installed on both the curtain wall as well as the window elements. And then the image on the right shows a graphical representation of where accelerations were determined to be occurring. And then the bubble, which is located over a sensor location, represents the quantitative amount of sound that is produced by that location over a period of 24 hours. So the larger the bubble, the more noise that particular location makes. So but the size of the bubble is also, so if you have a 1 decibel amplitude sound generated by that location 100 times, that size of the bubble would equal one noise that generated 100 decibels. So it's not you can't just look at the size of the bubble to determine the amplitude of the sound. It's more of over a 24-hour period average how much sound is generated by each location. But in any case, so you can see here, sensors 4, 5, and 6 coincide with the free end of the precast curtain wall panels. And you can see that each one of those, especially at location 6, generate quite a bit of sound, with location 6 actually causing the loudest sounds, which is expected since this is the free end of the panel and it's sliding on a steel plate. So you'd expect some sound to be generated there. And then you can also see that the ribbon windows, especially the sensors at 11 and 13, generated a significant amount of noise as well. This also made sense because the ribbon window is attached to the precast panels, and the windows span continuous across the joint where a lot of this movement is occurring. So as the precast expands and contracts, it places high stresses in the ribbon window framing. And these stresses are magnified at these precast panel joints. So we also measured the perceived amplitude of the generated noise. And for this particular project, we weren't able to correlate the amplitude to actual sound. We weren't allowed to make sound recordings due to the sensitive nature of the building. So we limited our sound meters to just measuring the amplitude, sound amplitude, and not actually recording a sound. So this made trying to figuring out, what sound actually correlated with our accelerometer readings a little bit difficult, because any sound, a door opening or somebody bouncing a basketball or anything, would have been picked up and recorded as a sound amplitude. So it took some time to look through the timestamps and figure out exactly which amplitude correlated with which acceleration. But we were able to do that. So it was noted that in general, the loudest sounds were about 15 decibels over the ambient noise. But there were some events, I'll show you in a little bit here, that were actually much more than that, up to about 85 decibels, which is about 40 decibels over the ambient noise. And then we also, by doing this correlation, we determined that the loudest noises were generally caused by the precast panel connections. So one interesting thing that we noted during our investigation was that at one location, one of the fixed connections was actually making quite a bit of noise. And this fixed connection is highlighted here by sensor 1. And you can see that its max sound pressure level or decibel level, it was generating about 27.5 decibels over ambient noise. And we concluded that there was probably a broken weld that had occurred at this location, which was causing the sound. And this same location is also the source of the loudest noise that we heard. And this was a free connection located on the bottom left-hand corner here. And this particular connection was causing about 40 decibels of noise to occur. And this was kind of a booming sound that was resonating throughout the whole building. So at the beginning of the project, we were told that the noise was only occurring typically during sunny days and when the sun was actually on that south wall. Our instrumentation identified that the sounds were actually occurring, throughout a 24-hour period, but that during midday, the sounds occurred much more frequently, and the noises, the period between noises was very close. So a lot of pops and pings, back to back. And then throughout the evening, the sounds there was the same amount of sounds, but they were distributed farther apart. And we were probably never told about the evening sounds because there was probably nobody in the building to hear them. And we also learned that the sounds first started at the ribbon windows, and then later in the day, they started to occur in the precast panels. And we attributed this to the precast panels having a much higher thermal mass than the ribbon windows, and therefore they were kind of slower to react to the thermal changes. And as you can see, at night, the sounds were just as loud, but they just occurred farther apart. And we attributed this to the heat gain or the thermal expansion occurring much higher or faster during the day because it was caused by solar radiation. And then at nighttime, the cooling was just through convection. So the elements lost heat more slowly and therefore generated the sounds farther apart. So our instrumentation for this particular project confirmed that, in fact, the sound was occurring both at the ribbon windows as well as at the precast connections. The precast connections were found to generate less frequent noise than the ribbon windows, but the sounds tended to be louder. And then at the precast windows, the sound was typically concentrated near the free ends of the precast panels. And kind of a recommendation that we provided for this particular project was to retrofit the free ends of the precast panels with some Teflon sliding pads to decrease the friction. And then kind of a more complicated recommendation would be to install split mullions at the ribbon windows where the ribbon windows cross the moving joint in the precast curtain walls. And with that, I will hand over the presentation back to Sylvan, and he can talk a little bit about the mitigation strategies that we've recommended in the past for this type of issues.
Great. Thanks, Jarkko. All right. Well, let's talk for a minute about some usual suspects. As we mentioned earlier, factors that we typically consider are wind loads and live loads, looking at how much deflection we anticipate in any given location, looking at solar orientation, interior and exterior temperatures, solar gain and thermal mass tend to play a role. As we discussed with the precast panels and the curtain wall systems, the thermal mass there changes their response time, thermal gain over the course of the day. So those different response times can exacerbate differential movement, right? You could have the same type of thermal expansion and contraction, but if it's not occurring at the same times, you get differential movement. And so expansion joints, sliding connections, and an important phenomenon to understand here is the stick-slip, what we call the stick-slip phenomenon, right, which is happening at the types of sliding joints like steel on steel plates, where we have very heavy cladding panels resting on a steel plate, that the coefficient of static friction is high, and so it's going to resist movement when it's sitting still. And as the stresses build up through the thermal expansion, eventually it's going to slip. And when it transitions from that stick condition to the slip condition, you get a popping sound. Okay, so when we're talking about wind loads and live loads, just to sort of understand what that means, here's some examples, right? Wind loads, we're looking at interstory drift anywhere from H over 600 to H over 100. So for a 14-foot interstory height, that could be 1/4 of an inch of drift. It could be well over 1.5 inches of drift. And understanding how much movement we're trying to accommodate can really help us anticipate where we're going to see that stick-slip phenomenon and how dramatic it will be. For live loads on floors, L over 360 is pretty typical for deflection limits, and over a 30-foot beam, that could be 1 inch of deflection. Sometimes there's going to be more conservative limits on that, like 1/2 inch for steel construction, or as little as 0.3 inches for concrete, and just understanding the movements, right, and accommodating those movements, and then helps us anticipate where we're going to see the sources of vibrations. I'll talk a little bit more about solar orientation because thermal expansion and contraction show up over and over again in our investigations of these issues. Solar radiation and color are closely linked issues here. So absorption factor, the amount of that light that's converted to heat, can be dramatically impacted by the color of the material. A white smooth surface, it might absorb 25% of that light, convert it to heat, or maybe 30%. If you go all the way over on the right side of this chart, a dark blue and black material, we're going to get well over 75% absorption factor. So we're getting much higher conversion of that incident sunlight into heat. So we're going to get significantly higher temperature rises in dark colored materials. Not just the color, also the nature of the material itself is going to affect how much of that solar radiation it converts into heat. On the far left, we're seeing things like polished or anodized aluminum. On the far right, we're seeing things like asphalt roof, iron, slate, blue and gray slate. So those materials are going to have a much higher absorption factor. That doesn't necessarily mean they're going to move more because the coefficient of thermal expansion varies widely between materials. The chart on the left here is an example of if we look at all of these different materials, wood, glass, PVC, steel, and we look at a 100-degree Fahrenheit temperature delta over a 32-foot length of material, we might get as little as 1/10 of an inch of movement, or as much as well over 1.5 inches of movement, because they have different coefficients of thermal expansion. And in this specific example I want to look at is the aluminum ribbon window system between precast concrete panels. So let's take a look at aluminum expansion over 32 feet. We're about just under 1/2 inch expansion with a 100-degree temperature delta. Take a look at the concrete structure, which is the precast concrete panel. We're looking at about 0.2 inches of thermal expansion. Same temperature difference, substantially different thermal expansion. So we're over 1/4 of an inch of difference in expansion rates there. So if those two systems are rigidly attached to each other and they experience the same temperature deltas, then we've got to accommodate that movement somehow. Well, there's a bunch of joints in that aluminum window system. If we've got 6 lights, those are about 5-foot lights there, we've got about 12 gaps. If each of those gaps is a 64th of an inch, we've accommodated a little over 1/8 of an inch of movement. Well, that's not quite enough. If those gaps are a 32nd of an inch, we double that gap size, but it's still pretty small. We've got plenty of room to accommodate that movement. That's just one example of how to think about where these differential thermal movements are being accommodated. One other thing to note, and I just think this is interesting, is that thermal expansion isn't necessarily the same in all directions. So wood across the grain has a much higher thermal expansion coefficient than wood parallel to the grain. Just because it's wood doesn't mean it's moving the same in all directions. Most materials aren't that way. Okay, so let's talk about how to mitigate, maybe eliminate, although that can be difficult, and hopefully avoid some of these issues. So we can reduce differential movement. We were just talking about how to anticipate the amount of differential movement and how material selection and color and adjacencies, and also where we place the different types of connections, whether it's a fixed connection or a sliding connection, can really affect the differential movement. And also where we put insulation. If there's a steel beam that's outboard of the insulation in the wall, it's going to experience much higher thermal movement, temperature differentials. So we can also install expansion joints, sliding connections. I think I talked about this already, coordination of movement. This is a picture of an expansion mullion, right, in a curtain wall or ribbon window system. It's designed to accommodate that movement along the length of it. Interestingly, we did have a problem on a project once where in the morning and the sun was shining on one side of those split mullions, the one side was expanding differentially from the other side, and then in the afternoon, the sun moved around the other side and created an issue. And so we were able to mitigate that by actually placing some insulation over the mullions. All right, this solution comes up quite often, which is reducing friction. So Teflon slide bearings are a great way to do that. And in a steel-to-steel sliding connection, there's a drawing of sort of a generic approach to installing a Teflon slide bearing. Right? You put a little shim in there, you epoxy a piece of Teflon sheet to it on both sides, and you've nearly or perhaps completely eliminated that stick slip phenomenon. And then just a parting note here, I want to go back to that metaphor of the piano, which is that we need to understand what's causing the sound, which may not be the same object that's the origination of the vibration. So we want to find out what string is being plucked that's making the noise. We also want to understand what the sounding board is that's generating the actual volume that we're hearing. And so we can mitigate the noise from both approaches. We can damp the vibration by damping the string. We can also damp the sound by adding mass or adding damping to the sounding board that's creating it. So with that, I think we're going to say thank you, everyone, for listening and joining us today. And I think we're ready to open this up to questions.
Yes, thank you, Sylvan. As a reminder, if you have a question, please type it into the Q&A box and hit submit. We'll try to get to all the questions submitted before the end of the hour, but if we don't have time to get to your question during the call, either Sylvan or Jarkko will follow up with you afterwards. Okay, let's go ahead and take our first question. How many days of monitoring are typically needed to identify the source of the noise?
Well, I can answer that, Liz. It kind of depends on the source of the sound and what is the energy that's causing the sound. So in an event like in that commercial facility, a lot of the noise was generated by, or thought to be generated by solar exposure. So we would need to monitor enough days to have a sunny day, a warm sunny day. So it really depends on the source of the sound and what is the thought that's causing, or what is the issue that's causing the sound. So in most cases, a few days or a day could work, or possibly a week. This kind of depends on what we're looking for and what is the cause that's causing that sound.
All right, our next question. Can you use vibration sensors to determine if and where, quote, banging bolt syndrome is occurring in a building?
Sure.
I'll answer that.
Yeah.
You go ahead, Sylvan.
I was just going to say, yeah, that's I would say that's a solid yes. I think that's the type of vibration, the type of problem that we're able to find with this methodology, which is the vibration monitoring. So there's a whole lot more nuance to it than that, but yes.
Yeah, and we've done that in the past, that specific issue. So it does work.
Okay, our next question. In hiring an AE team, what should an owner specify for a scope of work to make the AE team responsible for managing building sounds? For example, if a rain screen or curtain wall is to be specified.
This is a good question. Jarkko, I'm going to take a stab at this and then love to hear your thoughts on this as well. I think that what we often see in the specifications is a kind of a broadly reaching generic statement that the system shall not make sound due to thermal movement, as an example. And that's a tall order, and it can be difficult to anticipate that, especially when the problem is typically a coordinated problem between adjacent systems, right? So if you have one team that's focused on the curtain wall system and one team that's focused on the precast cladding panels and engineering their anchorage, they need to be able to, the window system itself might not be making noise, but when you attach it to this precast panel system, then it starts making noise. And so writing a spec that is going to address that coordination issue is challenging. I don't think I have a simple answer to that question, but I would want to take a look at some quality assurance measures where part of the installation might be a mock-up with monitoring, or you could include in the project scoping the type of investigative monitoring that we're talking about as sort of a preemptive. Hey, this may be an issue. We want to build into the project accommodations for chasing these problems down and installing mitigating measures.
All right, our next question. Are you ever asked to leave monitoring systems behind for mitigation strategy confirmation or just client satisfaction?
That's a great question as well. We can leave that systems behind, and I actually have a project coming up where we identified the source and then provided a recommendation. And then once they do the retrofit, we're going to install a mock-up retrofit, and then we're going to install the system to try to see how it performed. You know, if the mitigation strategy was successful in mitigating the sound. But yes, we can leave the equipment in place. There is a rental fee that will be associated with that, but it could be done. And also we could just come back and reinstall the sensors if something like a mitigation strategy has been implemented.
Okay, our next question. How much of an issue is humidity in expansion and contraction of wood frame structures?
Liz, would you read that question again, please?
Sure. The question is, how much of an issue is humidity in expansion and contraction of wood frame structures?
I'm going to go ahead and say I don't know the answer to that question. I think that when we look at expansion, if we're talking generally about expansion and contraction, moisture, expansion of wood due to moisture is a big concern, but it happens at a different rate than thermal movement. And so I think we wouldn't expect to see, I wouldn't expect to see the kinds of popping and pinging sounds that we see from thermal movement due to sort of rapid variation in temperature. I think we'd see longer term effects of moisture accumulation in wood. So I'm going to say I think it's a small factor, but I don't know.
Right. I'm kind of on board with Sylvan there. That I think the humidity would take longer to change the cause a volumetric change in the members. So therefore, I don't think it would be such a rapid release of energy that would cause a sound.
Okay. Our next question. What are the roles of different design professionals in reviewing the issues you discussed? The area seems outside the normal roles of both architects and structural engineers. This seems similar to the way both architects and engineers have developed forensic practices.
Can you repeat that question again?
Sure. The question is, what are the roles of different design professionals in reviewing the issues you discussed? The area seems outside the normal roles of both architects and structural engineers.
Right, and I think this is something that Sylvan touched on earlier. I think there needs to be interaction or coordination between the architect and engineer when they're designing their systems, especially the cladding systems as they tie to the structural systems. And maybe having a peer review of the whole system, could be something that could prevent some of these issues from occurring.
Yeah, and I think I want to add that this is tricky. I think this is a great comment, and this is tricky because just to use as a comparison, the type of water and air infiltration testing that we often see as quality assurance is something that can be done. It's something that's done in a laboratory in advance, right? And then it can be done in the field to verify that the installed conditions are also performing. I think for this type of sound, these sound issues, it's very hard to test the assemblies in advance in a lab. It really has to do with the entire assembly and how it's performing. And so anticipating when these noises are going to occur and where they're going to occur is difficult, and it's hard to put hard to get it all figured out ahead of time. So it's hard to put that responsibility on one part. But I think a consultant that does this type of forensic work would be an asset to a team that's trying to do their best to prevent these issues in the future.
Okay. So we are at 1 o'clock Central Time, so I think we'll wrap it up. I know we weren't able to get to all of these questions coming in, lots of good ones. And as I mentioned before, Jarkko or Sylvan will follow up with you after today's webinar to make sure that we've answered all of your questions. So thank you so much for joining us. We hope it's been educational, and thank you, Sylvan, and thank you, Jarkko, for the great presentation. As a reminder, you'll receive a follow-up email after today's presentation with a link to watch an on-demand version of the webinar at your convenience, and that email will also include a link to access related resources, including a PDF copy of the presentation, and a link to download your certificate of participation. Finally, there's a teal icon at the bottom of your screen, which will open a very brief survey about today's webinar, including an opportunity to suggest future WJE webinar topics, and we'd really appreciate any of your feedback. And if you have any other questions, please don't hesitate to reach out to me, Liz Pemper, at lpemper@wje.com. So thank you again so much for your time, and we hope you have a great rest of the day.